In today's session, we will discuss the factor of safety and compare it to the design factor. In a previous session, we defined that design factor is equal to the loss of function parameter over the maximum allowable parameter. The parameter could be a load or a torque or a stress. So if we choose the parameter here in Newton, then the denominator parameter should be in Newton. However, the stress may not vary linearly with load. It is more common to express the design factor in terms of strength and stress. And we know that the stress is equal to the force over area. So if we replace this parameter with the strength, and this is with the stress, and we calculate the design factor at the last stages of the design, it becomes the factor of safety. So the factor of safety and the design factor are interchangeable in meaning, but numerically they are different. Because let's assume you computed the stress based on a given dimensions, okay, and you found out that the diameter of the shaft, let's say, is equal to 47 millimeter. We said that you shouldn't order such kind of dimensions. You should use standard sizes, and therefore so for instance the diameter will become 50 millimeter. So now you need to compute based on the updated design the new design factor, which is becoming the factor of safety, and we will denote it by n, and it is equal to the strength, loss of function strength, over stress. Here is an example at which we will see how we could apply the factor of safety. A solid circular rod of diameter d undergoes a bending moment m of 100 Newton meter, and this bending moment inducing a strength of with this equation, using the material strength of 170 megapascal and a design factor of 2.5. So the design factor is equal to 2.5. Determine the minimum diameter of the rod. So we know that the design factor is equal to the strength over the stress, and this is equal to S over 16 bending moment over yd cube. This is over 1, which is equal to S by d cube over 16 m. Therefore, the diameter is equal to 16 m multiplied by the design factor over S pi. So we will substitute each parameter by its value. 16 times 100. Let me use parentheses. 100 Newton meter. The design factor is 2.5 over the strength 170 times 10 power 6 Pascal, 3.40, which is equal to, we can get this power 3 into radical square root with 3. If we calculate this diameter, the value will be equal to 0.02.8111 meter, which is approximately 21.1 millimeter. So this is the diameter, this is the recommended diameter based on this design factor. However, we cannot order to manufacture this rod, this circular rod of diameter 21.1. Okay, so we should use some standard sizes, and we see that from standard sizes it's recommended to have, if it is 21, something between either 20 or 22, so we'll be taking a 22. Okay, so the new diameter based on the new diameter is 22 millimeter based on standard sizes available. Okay, now the factor of safety due to this change in the diameter is equal to N, the strength over the new stress, which is 170 times 10 power 6 over sigma 16 m times 100 over pi. The new diameter is 22 millimeter times power minus 3 power 3, which is equal to 3.55. Okay, this is the new factor of safety, and this is the final value based on changes on the diameters and different variabilities in the design. Let's take another example and we see how the uncertainties in the dimensions could also affect the design process. So let's assume we have a shaft, and this shaft is under bending stress. Okay, so this bending moment will induce a stress in the inside of the beam, okay, and cause tension at the bottom and compression on the top. And this stress is equal to minus M, bending moment, M, multiplied by Y over, and Y is the distance between the neutral axis, okay, and the point we are calculating the stress, over I, which is the moment of inertia. If we assume this the cross-sectional shape of this shaft to be square, it would look like this. And now this would have a width of B, and a height H. Let's assume while manufacturing this shaft we have some uncertainties in the dimensions. So we have the height is equal to nominal height H1, and we say, like, what's the nominal? I mean, the difference between the nominal and the actual or the true. Let's say the nominal area. If we have an area of 10 meters square, and there is some variations will be on the area, it will not be exactly 10 meters square. Okay, so it would be plus minus some value. So we need to, at each section, we need to calculate the actual, okay, the actual or the true area at each section. But the nominal, the average, is 10 meters square. We don't take the uncertainties into consideration. We say nominal. Okay, so H, the height, is equal to a certain height plus minus, okay, this would be the true height, and this is the nominal height, which is plus minus some percentage. Let's say 3%. Of course, 3% of the nominal height. We have the base, the width is equal to B nominal base plus minus 5%, and let's assume that even the applied load has some variability. Okay, so M is equal to M1 plus minus 10%, and the strength of the material, we know the strength is the capacity of the material to hold a certain load, okay, before failure. Let's assume that we have the tensile strength. The strength is equal to the nominal strength plus minus 7%. Okay, and the objective here is to compute the factor of safety. So the question is, what is the factor of safety? Of course, in order to have a safe component, the applied stress over the shaft must be less than the strength of the material. So this should be known to us. So the maximum stress applied, or due to this bending moment, the maximum stress induced inside the component must be less than the strength. And of course, we will be taking, if the strength there is some variability, we will be taking the minimum strength to be on the safe side. So what is the stress? We note that the stress, the nominal stress, is equal to minus M1, the nominal bending moment, Y1 over I1. Okay, so what is Y1? If we take the neutral axis, this is the neutral axis, so we have a distance of h over 2 and downwards minus h over 2. So this is the distance y from the neutral axis. If we take h over 2, if y equal h over 2, then we are computing towards the compression, if we say the compression is from the top. But we are comparing because with the tensile strength, with the tension, so we'll be taking minus h over 2. So we have minus M1 minus H1 over 2 over I1. What is I1? I1 is the second moment of inertia, okay, or moment area moment of inertia, and we can compute it by let's assume that we need I, okay, around the neutral axis. This is the x-axis and this is the y-axis. Okay, I-axis around this plane, around the x-axis. We can take a small part, the area, small area, okay, very small area of thickness dy, on the y direction dy, okay. So this area dA multiplied by the distance square y, the distance y, multiplied by y square. And in order to compute it over all the cross section, we need to integrate it from h minus h over 2 to h over 2, minus h over 2 to h over 2. Okay, so this is equal to the integral minus h over 2 to h over 2 dA. The area of this small strip is equal to dy multiplied by the base. So height thickness, the thickness of this is dy and its width is b. So dy b dy y square. So we will rearrange this, and b y squared dy is equal to by cube over 3 from the integral of y squared is y, we add plus 1 over the total, which is 3, minus h over 2, h over 2. We substitute y by h over 2 and then minus h over 2, which is equal to b over 3, h over 2 power 3, power, yes, 3, minus h over 2 power 3, p over 3, h power 3 over 8, plus h power 3 over 8. That will yield 2 ph cube over 3 times 8, which is equal to ph 3 power 3 over 12. Okay, so this is the second moment of area. Okay, the moment of area, and it reflects, indicates how the area of the cross section is distributed relative to the a particular axis. That's why we multiplied a small area. We need to see how the area is distributed around this axis. We multiplied the area of this strip, we take a small one, then we integrate over all the whole cross section, multiplied by the distance. Okay, y squared. All right. So this would be ph cube over 12. So we have, of course, this is the nominal. We are using the nominal. All right. So we end up with 12 to 6 1 over h1 will remain h1 square. So this is the nominal stress. Now, if we want to take the maximum stress, we want to find the sigma max. In order to have the maximum stress, sigma max, we need a moment to be the maximum. We need the applied force. We take the worst case scenario, the maximum moment applied, over the smallest dimensions, okay, in order to have the sigma max. So in order to increase this, we need to increase m1 and decrease b1 and h1. So sigma max would be equal to 6 m1. Okay, we take the m1 to be the maximum. Okay, so I will calculate this. m1 m max would be m1 plus 10% of the m1, which is equal to 1.1 m1. Okay, so sigma max, in order to take the maximum moment, it should be 1.1 m1. 6 times 1.1 m1 over. For b1, we take the minus, right? We need to decrease b1. b1 is equal to, so b max, sorry, it is b1 minus the minimum, sorry. We need to minimize b in order to increase sigma. b1 minus 5% of b1, which is equal to 0.95 b1. h1 as well, we need the minimum value, minus 3%, which is equal to 0.97 square. Alright, we end up with 1.1 over 0.95 multiplied by 6m1 over p1 h1 square. And this is the nominal and this is the nominal stress, sigma nominal, right? So we determined the sigma max in terms of the sigma nominal. We have this additional parameter due to uncertainties. So we will continue our calculation on another slide. So we end up with sigma max in terms of the sigma nominal. And we notice that the worst strength will be the minimum. So we should be taking the minimum tensile strength. So we'll be taking minus 7% of the actual or nominal strength. So sigma minimum, or the strength minimum, is equal to S1 minus 7% of S1, which is equal to 93, 0.93. As nominal. Again, let's return to the condition to be on the safe side. Sigma max must be less than the strength. Sigma max must be less than or equal to S minimum. Sigma max is equal to 1.1 over 9597. This is square. You have square. Okay. So let me correct this. Yes. 6m1 or sigma nominal 0.93 as nominal. Now we can take this to the other side, the sigma. So we end up with 1.1 over 0.95, 0.97 square times 0.93 as nominal sigma nominal. Because those are normalized and they are on the same size, I mean the strength and the sigma both are nominal, then this is the factor of safety n. So the factor of safety n must be greater than or equal. We can calculate this and would end up with 1.323. So this is the factor of safety. So in this exercise we took into consideration the variabilities in the manufacturing dimensions, the variability in the load, the variability in the strength, and the strength can be measured, as we mentioned on previous sessions, from data in the laboratory or from other resources. Alright, so in this session we discussed the factor of safety and we compared it to the design factor. We said they are, in the meaning they are the same, but they are numerically different, at which the factor of safety is the final factor of safety in design, while the design factor do not take into consideration the variabilities that may occur at early stages of the design. Thank you.